Hello, everyone. We're going to go ahead and begin our review for exam 2. So we're going to have about 8 problems most likely in this video. And as a reminder, these 8 problems should look very familiar when you go to take the exam. All right, let's go ahead and get started. There we go. So example 1 was a problem that we did do in class. We have a rectangular box with a volume of 100 feet cubed, has a square base. Find a function that models its surface area S in terms of the length X of one side of its base. So this is one of our questions from the Chapter 2 application section. So we are given this rectangular box. It has a square base. One thing to remember about squares is that all sides are the same. So if we say that one side of the length of the base is X, then since it's a square, each side will also have length X. So that's one thing that we know about this problem already. And we know the volume of a box would be length times width times height. So we're going to use all this information together to go ahead and solve our problem here for our example. So, all right, we're going to go ahead and go on over to our notes so we can work on this problem. Ooh. All right, here we are with example 1. You probably just got a little preview of example 2 there. But all right, so for problem 1, we have our box here. We've drawn a picture of it. When it comes to problems like these, if you don't have a picture already provided or anything like that, it's always a really good idea to draw a picture. Even if you don't do any part of the problem, drawing a picture almost always guarantees you at least a point. So definitely draw the picture just so you can have a visual. It will help you out with figuring out the problem. So we said the volume of our box would be length times width times height. We also said that since the base of our box is a square, then each side of the square will be the same length. And we already said that one side of the length of the square base was X, which means that every side was X. And then we can label the height of the box as H for height. So we can go ahead. And we said that the volume was equal to length times width times height. But really what we're looking at here is that we've got the length right here and the width right here. And really the only thing left is the height. So we've got length times width times height, and we have variables for all of these things. So we say that this is equal to X times X times H. That's what volume is equal to. So even simplifying this a little bit further, the volume is X times X. Well, X times X is X squared times H. So volume is equal to X squared times H. And we were told in our problem that volume was equal to 100 feet cubed. So really, we care about the number value. The exponent of 3 on feet doesn't really mean anything other than it's indicating volume. That's all it's really doing, so we're not doing anything numeric with that. We just care about the value, which was 100. So we're saying that volume, which is equal to X squared times H, is equal to 100, because we said that the volume of the box was 100. So we can go ahead and we can just replace volume with 100 now. So we're saying 100 is equal to X squared times H. And we can write this over here. The volume was equal to 100 feet cubed. All right, so we've got this equation from volume and knowing what the box looks like, or relatively what the box would look like. This is just one example of what the box looks like. So we kind of hit a little bit of a wall at this point. We've got an equation for volume. We know what volume is, but we were asked for the surface area. The surface area of a box would be the area of every one of its surface. So surface area, which we're saying is S, has an equation. And we've gone over this before. You could look up this equation, have it on hand, on a note card or something like that for the exam. But the equation for surface area would be the sum of all the 6 areas of your box. So you have 2 squares and 4 rectangles. And since you have squares, we say that the area of a square would be side length times side length. And that would be x times x, which is x squared. And there's 2 of them, so it would be 2x squared. Then we have 4 rectangular sides, and the rectangular sides would be the width times the height, or the length times the height. So it would be x times h, and then there's 4, so it'd be 4xh. And we add those together to get the surface area. So that's how you get surface area, even if you don't necessarily have the formula on hand. But surface area would be equal to 2x squared plus 4xh. Because we have here area of square, and it's the base and the top. And then over here, we've got the area of the rectangular sides. So that's how we get our equation for surface area. So we have an equation for volume, then we have an equation for surface area, and the problem was asking us to find surface area in terms of x. So it doesn't want any h's. So that means that we can't have h. We need to replace it. So we're going to go ahead, we're actually going to highlight that in a different color. So we want to replace h with an expression of x. And luckily, we were given another equation. X squared times h is equal to 100. So we can go ahead and solve this equation for h. That's how we're going to replace h with an expression of x. So if we take 100 equals x squared times h, and we solve this for h, that means that we would divide each side by x squared. So this would in turn give us h is equal to 100 divided by x squared. So we're going to replace h with what it's equal to, which is 100 divided by x squared. So this means our equation will become s of x, because it is our surface area only in terms of x, would be equal to 2x squared plus 4x times h, which is instead going to be 100 divided by x squared. So we now have surface area in terms of x, but we do want to simplify. When it comes down to an exam, you always want to simplify if it is easy. If it's going to be incredibly complicated to try and simplify something, it's probably okay and you can leave it as is. But if it's easy to simplify something, you absolutely should be simplifying it. So in a case like this, we have 4x times 100 divided by x squared. That's fairly easily simplified. You multiply 4x by the numerator, divide anything that they have in common, and that's how we simplify. So that's what we're going to do. So we've got s of x is equal to 2x squared plus, and we multiply 4x by the numerator. So 4x times 100 would be 400x divided by x squared. So we see we have an x in the numerator and an x in the denominator. So we can cancel an x from each term. Now cancel the x and then cancel the squared. And this gives us s of x is equal to 2x squared plus 400 divided by x. And that was what our equation was asking of us, was to find that equation of surface area just in terms of x. So luckily, we don't have to do anything else with it. We just have to solve for the equation itself. So once you find that equation, you'd be done. So, all right, that's how we would go ahead and do a problem like number 1. So, all right, let's go on over back to our lectures so we can look at the next problem. All right, so here is example 2. So from the given quadratic function, f of x is equal to negative x squared plus 16x. We have 4 parts here. Part A, we're going to express f of x in standard form. Part B, find the vertex and the x and y intercepts of f of x. Part C, sketch a graph of f of x. And part D, find the domain and range of f of x in interval notation. So this is a pretty classic quadratic function problem here. You've had it on homework assignments, you've had it on the review. So we're going to go ahead and we're going to do all of these things. So all right, let's go on over to our notes. All right, so example 2, f of x is equal to negative x squared plus 16x. Our first part for part A is that we want to put it in standard form. And standard form of a quadratic equation is f of x is equal to a times x minus h squared plus k. And the vertex is located at h comma k. So we want to turn our equation into standard form. One thing to notice is that the form that we were given, which is typically referred to just as like a typical form or a decreasing exponential form or anything like that, just the form that you're usually going to be given. This is in the form of f of x is equal to ax squared plus bx plus c. That's what this form is already in. So we can go ahead and we can see that a, in this case, since there's no number there, it's technically a 1. So a would be negative 1. B would be 16, and then we don't have a value of c. That essentially just means that c is 0. So c is 0. So we know the values of a, b, and c, and we need to relate this to the values of h and k. A is the same value, so we don't need to do anything with the a value. But we do need to find h and k. And we have that. Let's go ahead and pick a different color here. We have that h is equal to negative b over 2a. And k, let's pick purple. K is c minus b squared over 4 times a. So we can go ahead and we can plug in our values of a, b, and c into the equations of h and k. So let's go ahead and start with h. We see that b is 16, so we're going to have negative 16 divided by 2 times a, which is negative 1. So we have negative 16 over 2 times negative 1. 2 times negative 1 is negative 2. So we've got negative 16 divided by negative 2. That would make that whole fraction there negative. So we'd have negative 16 over 2, which negative 16 over 2 would be negative 8. So it'd be negative 8, which has a double negative, which means that it's just 8. So h is equal to 8. Now we can go ahead and solve for k as well. So k, we have is c minus b squared over 4a. We said that c was just 0. We've got 0 minus 16 squared divided by 4 times a, which is negative 1. So we have 16 squared divided by 4 times negative 1. So we're going to go ahead and simplify. We have that 16 squared is 256. So we have 0 minus 256 divided by 4 times negative 1, which is negative 4. So you see that once again, this is going to become positive because we have a negative, or a double negative. So we're going to have 0. This is going to be minus negative 256 over 4, which just turns into plus. So go to the next line here. We have 0 plus 256 over 4, which just means that it's 256 over 4. And then we can use our calculators or our brains to find this value. And it'll be 64. So this means that, let's pull up our highlighter here, k is equal to 64. So we now have the values of h and k in our equation for standard form. So we're going to go ahead and plug that into the equation for standard form, and then we'll have our answer. So we've got f of x is equal to a, which we said was negative 1. We don't necessarily have to write the 1, but you can if you would like to. You can just write a negative. And then we have x minus h, which we said was 8, squared plus k, which is 64. So for part A, our answer would be f of x is equal to negative x minus 8 squared plus 64. So, all right. That was our answer for part A. Part B, we want to find the vertex and the x and y intercepts. So let's go ahead and move on. So part B, let's go ahead and do the vertex first. We said our vertex was at the point h comma k, and we know what h and k are, so our vertex would be 8 comma 64, since it's h k. It's a very poorly drawn k. There we go, that's a little better. So it's equal to 8, 64. So there's one. We also want the x and the y intercepts. There's going to be 2 x-intercepts, so we want to go ahead and find those. And there's 2 ways to find x-intercepts. You can take your equation from standard form and solve for x, or you can take your original function, set it equal to 0, and solve for x. So either way, you can use the original or you can use the standard form version, whichever one seems easier. I would say in general, standard form version is usually going to be easier. But for this specific equation, using the original function is actually a little bit easier, especially if your original function is able to be factored. You can factor it, set it equal to 0, and solve for x. And then it's not as bad. But if it's not going to be easily factorable, taking your equation from standard form, setting it equal to 0, and solving for x is probably a better choice. But all right, so we're going to grab the original function in this case, negative x squared plus 16x. So we're going to set that equal to 0. So we've got negative x squared, 16x is equal to 0. Now, in this case, we see there's a term in both one of these, or there's a variable in both one of these terms, x. Since x is in both of these terms, we can go ahead and we can factor an x out. So this would become x times negative x plus 16 equals 0. And then if either one of these, the x or negative x plus 16, if either of those were equal to 0, the whole thing would equal 0. So you would take them each separately and set them equal to 0. So for the one on the left, x equals 0, well, that's done. X is equal to 0. And then the one on the right, we've got negative x plus 16. We can go ahead, we're going to subtract 16 from both sides. We get negative x is equal to negative 16. You can get rid of the negative by multiplying by a negative 1 on each side, or dividing by a negative 1 on each side, or you can just get rid of both the negatives because that's what would happen if you multiplied or divided by a negative 1. So this means that x is equal to 16. We're going to go ahead, give those a little highlight. So our x-intercepts, we have the values of x, which are 0 and 16. Our x-intercepts themselves are 0, 0, and 16, 0. So those are the x-intercepts. Now we can go ahead and find the y-intercept as well. You find the y-intercept by letting x equal 0 in your function, and then finding what your function is equal to. So solving for f of x when x is 0. But another easy way to remember it is that the y-intercept is always 0, comma, c. And we're talking about the c from the original function at the top, at the beginning. And in our case, we said that c was 0. So that means our y-intercepts would be at 0, 0. Yeah. So our y-intercept is at 0, 0, which means that our x-intercept 0, 0 and our y-intercept 0, 0, same thing. So we see that the point or our function is going to go straight through the origin. So you can go ahead and write that. Ooh, wrong one. There we go. So our function crosses the origin. That's what it means when you get a point for x and your y-intercept being 0, 0. It means that your function has to cross through the origin in order for them to be the same thing. So, all right, we've got our vertex, we've got our x-intercepts, we've got our y-intercepts. Part C is that we want to sketch the graph. So we're going to go ahead, we're going to draw one, but you would be provided one on an exam. We're going to go ahead and draw the coordinate plane, and then we're going to fill in our graph. So let's draw up that coordinate plane real quick. All right, here's our coordinate plane. We're going to go ahead and we're going to plot our points. So whenever you're graphing a quadratic function, it means that you're graphing a parabola, a U. So you want to make sure that it looks pretty U-shaped as much as possible. But when you go ahead and you graph a function like this, it's always best to start with the vertex and then plot your intercepts. And then by that point, you should be able to connect up your graph pretty well. So let's go ahead and start with our vertex. We said our vertex was 8 and 64. Looking at our graph here, it is not to scale at all. We see that the y-intercept is going in tens and the x-intercept is going by ones. I only labeled the even numbers though. So we're going to go ahead, find 8 and 64, probably somewhere right about here. This would be our vertex, 8, 64. So it's always best to draw the vertex first. Then we said that we had our x-intercept and our y-intercept at 0, 0. So here's one of our points at 0, 0. 0, 0. And then we had our other x-intercept at 16, 0. So we're going to go ahead and fill that one in as well. It should be over here. So that's 16, 0. So we've drawn all of our points. Remember, this is a U shape, so it should look like a U. So we're going to connect up our vertex with our two x-intercepts and make it look as even as we can. Remember, you're not going for absolutely perfect, you are just going for accurate. As long as this is accurate, you should be good. You're not drawing a V, you shouldn't draw straight lines, but it should be curved. And one thing to notice is that that value of A in the front of our function here for the original and in the standard form is that it's negative. And if your parabola or your function begins with a negative sign, it means that you have an upside down parabola. So it should look like an upside down U instead of that like perfect kind of upward facing U. So it is going to be facing down, which makes sense for why our points are here. So we're just going to make sure that we connect the points in an upside down U form and we should go. So, all right, we'll connect the vertex with our intercept over here and our vertex with our intercept over here. Second to load there. Good enough. So we've connected the points, and then the last thing you want to do, since this is a graph that it would be continuing on forever, so you just add those little arrows at the end. So you want to add the arrows as well there. So we can add those arrows on once again, not perfect, just accurate. So there we go. That is roughly what our graph would be looking like. So just as a reminder, it's always good to do vertex first and then all of your intercepts. Whether or not you have, the same intercept for one of your x-intercepts and a y-intercept, or if you have 3 different ones, you just want to definitely make sure to graph all of them and then just connect with a smooth curve. It should be looking like an upward facing U or a downward facing U, one of those options there. Remember, this is not a line, connecting with lines. It should not look like a V at all. It needs to be curved. It needs to be looking like a U. So just remember that. All right. Since we are taking our exams on paper and mostly not a website, we don't have that automatic kind of drawing and parabola tool for us. We will need to know how to do it by hand. All right. Then the last part of the question was part D, and was asking for us to find the domain and the range. So domain, when it comes to functions like these, very easy. The domain of any polynomial, meaning that no fractions, no fraction bars, no square roots or anything like that, it's just negative infinity to infinity. So when it comes to quadratic functions like this, domain is very straightforward, negative infinity to infinity every time. Then we also want to find the range. Now the range you can find either by the graph or you can remember some specifics. We said that if the value of a was negative or less than 0, it means that you have a maximum, or that your range would go from negative infinity up to k, including k. And we said that if a was positive, meaning that it was greater than 0, then you would have a minimum, and your range would go from k to infinity, including k. So in our case, we said that a was negative. There's a negative 1 outside of our function there. We said a was negative 1. So our range in this case, and we can get this from looking at the graph as well, we see that the numbers would go down infinitely towards negative infinity, and we have a cap or a maximum there at the value of 64 because it goes to k. So our range would be negative infinity to 64. And we always want to include that value of k since we do have a defined point there. But we'll write that right below here. We say if a is less than 0, the range would be negative infinity to k, including k. If a is greater than 0, meaning that's positive, your range would be k to infinity, including k. So that's how you would find your range. And you can find your range by looking at the graph and finding the range, or you can use this little reminder here as well. So all right, that wraps up example 2. We went ahead, you took our quadratic formula, we put it in the standard form, we found the vertex, the x-intercepts, we graphed it, and we found the domain and the range. All right, so we're going to go ahead and go back on over to the slides. We can go on to our next problem. All right, example 3, we want to describe the end behavior of each polynomial. We have part A is y is equal to x cubed minus 8x squared plus 5x minus 16. And B, we have y is equal to negative 5x to the power of 4 plus 15x plus 100. So when you want to find end behavior, it's really helpful to have that chart that we looked at in section 3.2. This is the chart if you forget it. So our chart is telling us that we have some random polynomial here, p of x is equal to a sub n times x to the power of n plus, and we put 3 dots because it doesn't matter what comes after the first term. Nothing matters after that. It only matters about the first term, the coefficient or the number in front of x, and its degree. So we have these two kind of characteristics here. Either your leading coefficient is positive or it's negative, meaning this value of a sub n right here. It's either positive, meaning that it doesn't have a negative sign, or it's negative, meaning that it has a negative sign. So it's pretty easy to tell. Then we have x to the power of n, where we have n is the degree or the highest numbered exponent. And we see that n can be an odd degree, meaning that n is an odd number, 3, 5, 7, 9, 11, so on, so on. And we have an even degree, n is an even number, meaning that this is, 2, 4, 6, 8, 10, 12, so on, so on. So you'll find each one of these characteristics. You'll find whether or not the leading coefficient is positive or negative, and then find if the degree is even or odd. And then you'll find the box that corresponds to both. So as an example, we go back. We see that example 3, part A, we have y is equal to x cubed minus 8x squared plus 5x minus 16. Remember, the only thing that matters is that very first term. So we only care about x to the power of 3. And we say that if there's no number in front of the x, it technically just means it's 1. So our coefficient is 1, and our degree is 3. So we'll go ahead, go to our chart. We see that our leading coefficient is 1. It's positive, it's not negative. So it would be positive here. and then we had an odd degree, which is our first column. So we see we have the first row and the first column, those cross right here. So that means our end behavior for something like part A would be that y approaches infinity as x goes to infinity, and y approaches negative infinity as x approaches negative infinity. The hint here is that they're the same. You would be given usually x, and you would need to declare y. So if x is going to infinity, so is y. If x is going to negative infinity, so is y. So let's go ahead and just write that in our notes for part A here. All right, we're just going to write this down. We see that y is equal to x to the power of 3 minus a bunch of other stuff, doesn't matter. So we said that the coefficient is positive and has an odd degree. This in our chart there meant that they were the same. So as x goes to negative infinity, so would y. And as x goes to infinity, so would y. So we've got our answers there. Y goes to negative infinity as x goes to negative infinity. Y goes to infinity as x goes to infinity as well. So let's go ahead and go back to our chart to look at part B. All right, we said part B was y equals negative 5x to the power of 4 plus 15x plus 100. We see that number right in front of x there is a negative 5, so it's negative. And our highest power is 4, meaning that the degree is 4. So looking at our chart, we have a leading coefficient that is negative. We said that it was negative 5. And the degree was even. It was the degree of 4. So we look where these two columns and rows cross, which is this one down here. So we see that y approaches negative infinity as x goes to negative infinity, and y approaches negative infinity as x approaches infinity. So in this case, with a negative coefficient and an even degree, y would always go to negative infinity, no matter what x goes to. So let's go ahead and just write that down in our notes. All right, we said that our function here had a coefficient that was negative and had an even degree. So negative 5 was in the front and the degree was 4. And that means that y always goes to negative infinity. So we have y approaches negative infinity and negative infinity, no matter where x goes. So there we go. That's our end behavior there. Y approaches negative infinity as x approaches negative infinity, and y approaches negative infinity as x approaches infinity. So, all right, let's go back over to our slides to continue on. All right, so we just finished up in example 3. This isn't a bad thing to have during the exam, but also if you remember kind of what this looks like and the little clues, same, opposite, y always goes to infinity, y always goes to negative infinity, that could be very helpful as well for the exam. All right, so example 4, we have two polynomials, p of x and d of x are given. We're going to use synthetic or long division to divide p of x by d of x and then express the quotient in either form of the division algorithm. So we're going to go ahead and we're going to show both, just because you'd use either one on the exam. So you always want to use the one that you feel like you are better at. So we're going to go ahead, we're going to do both, and then we're going to express our answers. We're going to write both forms of the division algorithm, but once again, it would be up to you. The division algorithm will also be given to you on the exam, so you do not need to have it memorized or written down or anything like that. So yeah, let's go ahead and go on over to our notes to solve this problem. We've got p of x is equal to x cubed plus 8x squared minus 5x minus 12, and d of x is x plus 2. So, all right, let's go and head on over. All right, so we're going to go ahead and we're going to start off with long division for our problem. Now, we did do long division section 3.3, so I will still be going through the steps, but I will not be explaining them as much. If you need more of that explanation, you can go back to watch section 3.3 lecture video. So, all right, starting off with long division. Long division is longer than synthetic division, but it always works. Synthetic division only works for if your divisor or d of x is x plus or minus a number, which in our case it is. But if it wasn't, you would have to use long division. So long division works all the time, but it is longer, a little bit more tedious. All right, so we've got x plus 2 dividing into x cubed plus 8x squared minus 5x minus 12. Now, we'll review any missing terms. You would want to fill that in with a 0x to whatever power it is that it's missing. In our case, we don't have any missing terms, but if we did, we would want to write 0x to whatever power it was supposed to be there. So, all right. For our very first step in long division, you always want to divide the the leading term of the dividend divided by the leading term of the divisor. Leading term of the dividend would be x cubed. Leading term of the divisor would be x. So we want to divide x cubed by x, and this will give us x squared. And this is going to be the first answer that we have in our quotient. So our quotient, which goes above the house there, is x squared. Then we're going to go ahead and we're going to multiply. We're going to multiply x squared by our divisor. Then we're going to go ahead and we're going to subtract those statements from our dividend. So we're going to multiply x squared by x. That gives us x cubed. X squared times 2 would be plus 2x squared. Now, if you've done the long division right, the first terms cancel each other out. That means that you did it correctly. If they didn't cancel each other out, you did something wrong. So go back and look over it. So, all right, first terms should always cancel out if you are doing long division. Then we have 8x squared minus 2x squared. So 8 minus 2 is 6. So we've got 6, and the x squared comes along for the ride. Then we want to go ahead and carry down that next term, which is minus 5x. And now this is our new dividend, and everything that we did, we will repeat. So I'm going to go ahead and clear those. Now we take the leading term of our new dividend, which is 6x squared, and divide it by the leading term of the divisor. So we've got 6x squared divided by x would be 6x. So that's the next term of our quotient, plus 6x. Now, whether or not you're going to write plus or minus, it follows the sign of that value that you just found. So we just found 6x. Since it was positive, that means we're going to write a plus. All right, then we take 6x and we multiply it by our divisor and subtract it from the new dividend. So, all right, 6x times x would be 6x squared, and 6x times 2 would be 12x. So, like we said, if we did it right, those first terms should cancel each other out, which they did. Then we have negative 5x minus 12x. Now, you're really just doing this operation with the coefficients, not necessarily x. The x and its potential exponents would just follow along with whatever your value was. So really, we're looking at negative 5 minus 12, which is negative 17. And x comes along for the ride. All right, so we've got a negative 17x, and we carry that last value down there, that minus 12. And we repeat everything again. We divide, clear those out. We're going to divide the new term of the dividend by the leading term of the divisor. So we're going to have negative 17x divided by x gives us negative 17. So the last value of our quotient would be negative 17. Then we're going to go ahead and multiply that by our divisor and subtract it from the new dividend. So we have 17 times x minus 2, and subtract that from our terms there. So negative 17 times x would be negative 17x. And negative 17 times 2 would be negative 34. So we have negative 17x minus negative 17x. So we have a double negative here, which means that's really plus. Those cancel, which means that we did it right. Then we've got negative 12 minus negative 34. So since it's minus negative, it's really plus. So this is really negative 12 plus 34. So we're going to go ahead and subtract. Or sorry, we're going to go ahead and add. It's not subtract anymore. Negative 12 plus 34 gives us 22. So looking at our problem here, we have this final 22, and we can't go any further. There's no more terms that we could potentially divide into with x plus 2. Our answer is too small, which means that this is officially the remainder, or r of x. And this top portion will be the quotient. All right, so we're going to go ahead, we're going to write it in the two forms of the division algorithm, and then we'll do synthetic division as well, just to show how we would do that. So we have our quotient, we have our remainder. Our division algorithms are P of x divided by D of x is equal to Q of x plus R of x over D of x. Our quotient is that Q of x there. So we can fill in everything into this form because we know all of the terms. We have P of x, D of x, Q of x, and R of x. So this form would look like x cubed plus 8x squared minus 5x minus 12, all divided by the divisor, which was x plus 2, is equal to the quotient, which we said was x squared plus 6x minus 17 plus the remainder 22 divided by the divisor x plus 2. So that would be one of our answers. You just need to pick one. Doesn't have to be necessarily this one. So there's another one. Our other one is, and we're going to need a little bit more room for this one, P of x is equal to D of x times Q of x plus R of x. So in this case, we would write x cubed plus 8x squared minus 5x minus 12, which is P of x, is equal to D of x plus 2 times our quotient x squared plus 6x minus 17 plus the remainder, which was 22. So this would be the other form that we could write our answer in. So remember, even if you do the problem, you have to write your answer in one of these forms in order to receive full credit. All right, so those are what our answers would look like. That was with long division. Let's go ahead and show synthetic division as well. We already know what the final answer should look like, but we're going to go ahead and show synthetic division. So synthetic division is shorter, but it only works with the divisor if the divisor is x plus or minus a number. In our case, we have the divisor was x plus 2, so it totally works here. So we're going to use the divisor and the coefficients of our dividend. Remember, that's how we do synthetic division. And when we do it, we want to find this value of c. And your value of c would be your divisor set equal to 0 and solve for x. So in order to find c, we would take our divisor, d of x, set equal to 0, solve for x. So in our case, we've got x plus 2 set equal to 0. We're going to solve for x. X would be equal to negative 2, which means c is negative 2. All right, so our value of c is negative 2. When you set up your synthetic division, you would write c, or your value of c, which we are going to do over here. We said it was negative 2. And you draw this upside down house. Then you write your coefficients of your dividend. So our dividend was x cubed plus x squared minus 5x minus 12. So our first coefficient would be 1, since there's no number in front of x cubed. And then we have 8, negative 5, and negative 12. So we write our coefficients, and we draw an extra line in there so we kind of have some rows. Your first step is to carry that first number down to the bottom. So you just take it straight down to the bottom there. Then you multiply your value of c by that number you just added in the bottom row, and add that number to the middle row below the next coefficient. So negative 2 times 1 is negative 2. And then you add the column. So 8 plus negative 2 would be 6. And then everything repeats. You take the value of c, multiply it by that number in the bottom row, write your answer in the middle column beneath the next number. Negative 2 times 6 would be negative 12, and you add the column. -5 plus -12 would be -17. Then one more time, -2 times -17 is positive 34. Add the column. -12 plus 34 would be equal to 22. So we go. So we found all of the values of our quotient and our remainder. So when you do synthetic division, it can be a lot faster, but you need to remember how to interpret your answer. That very final number there at the end is the remainder, r of x. Everything else is just the coefficients of the quotient. These are all the coefficients of the quotient. So you already have r of x, it's the very last number. Now to find the quotient or interpret the quotient, once you put a big giant circle around r of x, that last number, you would start from that number and go to the left. And every space you go to the left, you're going to add on an x to the power of something. That's going to increase by 1 each time. The very first one you put on is the number just to the left of the remainder. And it starts with x to the power of 0. Then you're going to add 1 for every space you go to the left. So the next one will be x to the power of 1, x to the power of 2, and then we don't have any more. So there we go. X to the power of 0 is really just 1, and x to the power of 1 is just x. So 1x squared is x squared. And then once again, you're going to follow the signs for any addition or subtractions. So since 6 is positive, it would be plus 6x. And since 17 is negative, it would be minus 17, which is what we said the quotient was all the way up here. So this was our quotient q of x. And then you would write your answer in one of the forms of the division algorithm. So we definitely see that synthetic division was a lot faster and a lot simpler, but you do have to interpret at the end. So it's really key there that you know how to interpret your answers, or else you won't get full credit for not being able to know what things are what in your answer. But you always want to go with whatever one you feel more comfortable with and whatever you think you are better at. So if you're better at long division, by all means, use long division. If you like synthetic division more and you like synthetic division, then you can use synthetic division as long as the divisor is x plus or minus a number. So, all right, let's go ahead and go on back over to our notes. All right, so that was example 4. We can go ahead and move on to example 5. Example 5, we want to find a polynomial of the specified degree that satisfies the given conditions. We have degree 4 and the zeros -1, 0, 1, and 3. So we want to create a polynomial that has these specific requirements. So we're going to go ahead and go on back over to our notes to work on this problem. All right, so here we are, problem 5. We have polynomial requirements. We want a polynomial of degree 4, and the zeros are -1, 0, 1, and 3. So we want to create this polynomial that would meet all of these requirements. So since we're given the zeros, we know that x minus a 0 would be a factor of a polynomial. So that means our first step in creating our polynomial would be having the factors x minus each one of those numbers. And there's 4 zeros, so we're going to write x minus 4 times. So we've got x minus, leave a space, x minus, leave a space, x minus, leave a space, x minus, leave a space. Then you'll take each one and put it in that place that we left blank. So we get x minus -1, x minus 0, x minus 1, and x minus 3. All right. So we have all of those numbers placed down now. We simplify this a little bit. We get x minus a negative number and x minus 0. X minus 0 is really just x. I personally like to put a plain x just at the beginning. X minus -1 is really x plus 1. Then we have x minus 1 and x minus 3. So since we have these terms, we want to multiply these together. Now, this would most likely use foiling, but we can also use another strategy. And what we notice right here is that we have x plus 1 times x minus 1. Now, this is called the difference of squares. And we've mentioned it quite a few times, but it's very useful in chapter 3 because you see a lot of factoring, you see difference of squares come up a lot. Difference of squares states that something that looks like x squared minus a squared would factor into x plus a times x minus a. And it works the same way backwards. And in our case, we've got x plus 1 times x minus 1. So in our case, a is 1. So that means our polynomial could be simplified pretty quickly without using any sort of like foiling techniques or anything like that. X plus 1 times x minus 1 would be x squared minus 1 squared. 1 squared is 1. So this is x times x squared minus 1 times x minus 3. So we see that using the difference of squares kind of sped up this problem a little bit because we didn't have to do any foiling or the square method or the triangle method or whatever method that you use for multiplying polynomials together. Kind of got to skip that step a little bit. And now you have a few options. Since it's multiplication, you could just multiply straight across. You could distribute the x into the x squared minus 1. You could distribute the x into the x minus 3. You could multiply x squared minus 1 times x minus 3 first, and then just put in the x at the end. It's really going to be up to you. There's no wrong order in multiplication. So you can multiply in any order that you'd like, and it would always work out. For us, I'm just going to multiply the more difficult parts first, and then I can just add in the x at the end. So I'm going to multiply the x squared minus 1 and the x minus 3 together first. So if we FOIL these out, because that is the method that I typically prefer, if we FOIL, that'd be first, which in our case would be x squared times x, which would be x cubed. So first, outer, so you multiply the outer terms, negative 3 times x squared, you get negative 3x squared, times inner, negative 1 times x would be negative x, times last, negative 1 times negative 3 would be positive 3. And the rest of our polynomial is still the same. We still got p of x is equal to x times all of that. So we have x times x cubed minus 3x squared minus x plus 3. Last step here is that we're just going to distribute that last x into each one of our terms. So this would look like p of x is equal to x to the power 4 minus 3x cubed minus x squared plus 3x. So we developed a polynomial from the information that we were given. Let's go back up to our requirements and see if we met them and see if there's anything else. So our requirements were that we had a polynomial of degree 4, which we, there we go, which we do. The highest exponent on our polynomial is 4. So we have degree 4. And we said our zeros were negative 1, 0, 1, and 3, which we really did in this step right here. That's where we plugged in those zeros. So that requirement is also met. Those are the only two requirements, which means that this polynomial would be our final answer. So, all right. That was problem number 5. Let's go ahead and go back over to our slides so we can work on the next problem. All right, so example 6, we have a polynomial p of x is given. P of x is equal to x to the power of 4 minus 625. For part A, we're going to factor p of x into linear and irreducible quadratic factors with real coefficients. In part B, we're going to factor p of x completely into linear factors with complex coefficients. Now in section 3.5, we learned about the imaginary number I, and how if we multiplied I to any real number, it would create a complex number. And the only time that we use complex numbers is in section 3.5. So if we're not talking about section 3.5, we do not want complex numbers, no numbers with i's in them. So the key to knowing on whether or not you should include an I is that your problem will specifically have the word complex. So in example 6 here, we see in part B, there is the word complex, which means that we should not have an I until we get to part B. And then any other time, we would never include an I. So the only time that you would include complex numbers or the imaginary number I is if you see the word in the instructions very specifically say complex. So that's the key word there for knowing if you should be including an I or not in your answers. So we will include imaginary numbers in part B, but not in part A. That's what irreducible means. Irreducible quadratic factors are the factors right before you would have to have an I. So it's basically anything that's going to be, or anything that's going to have a complex 0 or anything like that. And then part B, you actually find those factors. So part A is really most of the way there, and then part B is kind of just that last step. So let's go ahead and do this problem in our notes. All right, so example 6 here, we have p of x is equal to x to the power of 4 minus 625. Now we've got the difference of squares here on the side and the sum of squares. So we're going to use both of these in our problem, but first things first, we've got x to the power of 4 minus a big number, 625. So we need to find a way how to factor this. And if we look at our problem, we look over to the difference of squares, what we see here is that if we have x to the power of 2 minus some number to the power of 2, that would factor into x plus a times x minus a. Now, just as an example, let's go ahead, let's take p of x, and let's just say it's x squared minus 625 instead. We're going to cut the exponent in half. And this works for other factoring ways as well, not just for the difference of squares. So if you ever have a polynomial that has x to the power of 4 and then x to the power of 2 and then a constant number, you can factor this in a very similar way that we're about to see here. So let's just use, as an example, what would happen if this were x squared minus 625? So we can go ahead and we say, this is x squared minus 625. And if we wanted to use the difference of squares, we would need to know if 625 is the square of any number. So we can go ahead and we can take the square root of 625. And if you do, you would see that 625 is the square of 25. So this is really x squared minus 25 squared, which this is the difference of squares. That means that this would factor into x plus 25 times x minus 25. Now remember, this was just an example. We said, hey, what if p of x had half the exponents instead? It was x squared instead of x to the power of 4. But the thing is, if we pretend this and say it's x squared instead, our answer is almost the same. The only thing that changes is that in our factored form, x would also have to be squared. So for p of x for us, which has x to the power of 4, it would factor into x squared plus 25. And x squared minus 25. So that is going to be the difference. We're going to write that in red here instead. So that is the difference. You can use the difference of squares if you kind of see a question that looks like this. You can use the difference of squares the same way. It's just that when you factor, it would be x squared instead of just an x. That's the only difference. And same thing for any other factoring method. If you see that the exponents on x are doubled from what you're used to, factor it the same way, make the exponents squared instead of x when you factor. All right, we get p of x is equal to x squared plus 25 times x squared minus 25. Now for part A, we want to factor into our irreducible quadratic factors and our real numbered linear factors. So in this case, x squared minus 25 is once again the difference of squares. And x squared plus 25 would be the sum of squares. And in part A, we don't want any i's. We want irreducible quadratic factors and real numbered linear factors. So that means that we are not going to factor x squared plus 25 for part A because we do not want complex numbers. We want complex numbers for part B. But we can still factor x squared minus 25 using the difference of squares. So p of x would be equal to x squared plus 25. And we know that 25 is really 5 squared. So x squared minus 25 using the difference of squares would be x plus 5 times x minus 5. And that's how we get that x squared minus 25 factored using the difference of squares. So, all right. So what we notice here is that x plus 5 and x minus 5, these are real numbered linear factors. And we know that if we factored x squared plus 25, that would give us complex linear factors, which is what we do not want. That's part B. So x squared plus 25 is our irreducible quadratic factor. So for part A, that is our answer because we don't want complex numbers. But in part B, we do. So in part B, you're just going to take your answer from part A, p of x, is equal to x squared plus 25 times x plus 5 times x minus 5. And you are going to break x squared plus 25 into its factors, which we use with the sum of squares. So the sum of squares says that x squared plus a squared would be factored into x plus ai times x minus ai. And I is the imaginary number of the square root of -1, so I is always the same, it's just I. And the value that changes is a. And we said that 25 is the square of 5. So really a is 5 in this case. So when we factor our polynomial, we get p of x is equal to x squared plus 25 would turn into x plus 5i. X plus ai, we said a was 5, and x minus 5i. And we still have our x plus 5 and our x minus 5 on there as well. And what we see here is that we now have complex numbered linear factors. And we still have the real numbered linear factors as well. So this, in this case, would be your answer for part B. So we see that part A is really most of the solution, and then part A is kind of that one extra step of breaking it down into its complex numbers or complex roots or complex zeros. So that's how we would do a problem like this. Using the difference of squares for most of your exam is going to be incredibly helpful to you. So knowing the difference of squares is very helpful. It's a very quick factoring technique, so you don't actually have to factor anything. It really just boils down to knowing what it looks like and being able to use it. And the sum of squares is really helpful in a problem like this because it works the same way as difference of squares, but only if you want complex numbered factors. So only if you are specifically asked for complex numbered factors will you use the sum of squares. If you are not being asked for complex numbered linear factors, do not use the sum of squares. You would end it at basically the answer for part A. You would not go any further unless specifically asked. So, all right, that was example 6. Let's go on back to our notes so we can go on to the next problem. All right, example 7, we're going to find the common factors in the numerator and denominator, and then we're going to find the intercepts, asymptotes, domain, and the range. So our function here is r of x is equal to x squared plus 5x minus 14 divided by x plus 1 times x minus 3 times x plus 7. And we have the graph given to us right here. We have our function here. We see some asymptotes happening, some 2 vertical asymptotes, 1 horizontal asymptote. See there's a hole right here, so we want to make sure to look out for that when working on our problem. And yeah, all right, let's go on over to our notes so we can go ahead and work on this problem. All right, so example 7 here, we have a rational function, x squared plus 5x minus 14 divided by x plus 1 times x minus 3 times x plus 7. Whoop, there we go. So what we're going to do is at step 1 with rational functions and finding most of its details, things like x-intercepts, y-intercepts, common factors, vertexes, or sorry, not vertexes, asymptotes, vertical asymptotes, horizontal asymptotes, and the domain and range, your very first step is that you want to factor as much as possible. And we see that our denominator is already factored, so we don't have to factor the denominator, but our numerator still needs to be factored. We look at it, we imagine it probably can be, so let's see. Step 1. A factoring technique that you can use is that if you were given some function f of x is equal to ax squared plus bx plus c, really, this often tends to look instead more like, let's erase that real quick, x squared plus a plus b times x plus a times b instead. So what we just saw that ax squared plus bx plus c, this is another way of writing your function. And this helps with factoring, because a problem like this would factor into x plus a times x plus b. So really what you're looking for is that you want 2 numbers that multiply to that last number, and those 2 numbers also need to add to the one in the middle, the one being multiplied by x. So in our case, for step 1, we've got x squared plus 5x minus 14 in the numerator. We want to know 2 numbers that multiply to negative 14 and also add to 5. So we can think of all the factors of negative 14, 14 and 1, 7 and 2. So really the only ones there. 7 and 2, if you subtract, say, 2 from 7, that gives you 5. So 2 numbers that multiply to negative 14, that means that the 7 or the 2 has to be negative, and it has to come out to a positive 5. So in our case, this would end up being a positive 7 and a negative 2, which means that our numerator will factor into x plus 7 times x minus 2 divided by x plus 1 times x minus 3 times x plus 7. So right off the bat, we see we had a common factor, and that was part of our question, to find a common factor. The common factor would be x plus 7, because it's in the numerator and the denominator. And since they're in both, they would cancel each other out. So this tells us that the common factor was x plus 7. Now, if you have a common factor and you cancel it out of your numerator and your denominator, technically you would originally have had a vertical asymptote where x was negative 7 in this case. But since you were able to cancel it, it really doesn't affect your function anymore. But even though you cancel it, you can't completely ignore it. We would say in this case that you would have a hole at x equals negative 7. Take your factor, set it equal to 0, solve for x. So we have a hole in our function at x equals negative 7. But our resulting function now is r of x is equal to x minus 2 divided by x plus 1 times x minus 3. And we have a much simpler problem now in this case. So we can remove this step if you want. You can leave the step there. We're not graphing a function or anything like that. So you can still follow the steps that we have from section 3.6, or you can just solve for the things it's asking for. So we've got our function r of x here. We're being asked to find the x-intercept. So we want to find the x-intercept. X-intercept is found by setting the numerator equal to 0 and solve for x. So in our case, our numerator is x minus 2. So we would have x minus 2 set equal to 0. We're going to solve for x. We're going to add 2 to both sides. We're going to get x equals 2. There we go. X equals 2. That's the x-intercept. The actual intercept itself would be at 2, 0. So our x-intercept is at 2, 0. Let's go ahead and write that 0 a little bit better there. I messed up it a little bit. There we go. So our x-intercept is at 2, 0. Now we can go ahead and find the y-intercept as well. Our y-intercept we would find by letting x equal 0 and solving for r of x. Typically, if you have expanded forms in the numerator and the denominator, it would just be the fraction of those two numbers at the end. But in our case, we actually don't have factored out or expanded expressions. We have x plus 1 times x minus 3. So it's easier to just plug in 0 for x, solve for r of x. So for our y-intercept, we would set x equal to 0 and solve for r of x. So r of x would be equal to 0 minus 2 divided by 0 plus 1 times 0 minus 3. 0 minus 2 is negative 2. 0 plus 1 is 1. And 0 minus 3 is negative 3. This is negative 2 over negative 3, which is equal to 2 over 3. This means that our y-intercept, oh, come on. There we go. Will be 0, 2 over 3. So there is our y-intercept. So we found the common factor, we found our x-intercept, we found our y-intercept. Now we want to find the vertical or vertical asymptote and the horizontal asymptote. So the vertical asymptote is found by setting the denominator equal to 0 and solving for x. So you take the denominator equal to 0, solve for x. Our denominator was x plus 1 times x minus 3. And luckily it's already factored, so we can set them each equal to 0 separately. Because we know if either one of those factors were 0, the whole thing would be 0. So we solve for each. We would get x plus 1 is equal to 0 and x minus 3 is equal to 0. For the one on the left, we would subtract 1 from each side to get that x is equal to negative 1. My handwriting is getting progressively worse here. So we got x equals negative 1. And add 3 to both sides on the right to get that x is equal to 3. So for your vertical asymptote, you would just name both. X equals negative 1 and x equals 3. You probably typically write it a little bit more like x equals negative 1 and then just comma 3. But either way, those would be your vertical asymptotes. Then we want to find the horizontal asymptote as well here. So with our horizontal asymptote, we said that it depends on the degree of your numerator and the degree of your denominator. So if we look at r of x, we would see that the degree in our numerator is 1. So n is 1 in the numerator. then we don't have an expanded version of x plus 1 and x minus 3. You could definitely expand it if you wanted to, but you don't necessarily have to, because the degree of your polynomial is equal to the number of factors you have. So in our case, our denominator has 2 factors, which means that the degree of our denominator would be 2, the same thing. So when finding your horizontal asymptote, you would use that chart that we used back in section 3.6. You'd use that chart to see if the degree of your numerator n was greater than, less than, or equal to the degree of your denominator, which is m. So in our case, we say n and m. Since n is 1 and m is 2, n is less than m, which in that case tells us that our horizontal asymptote is y equals 0. The horizontal asymptote in that case is y equals 0. Now the last thing we wanted to do was determine the domain and the range. The range has to come from looking at the graph. So we're going to take a peek at the graph back from our notes, but we want to go ahead and we're going to write out the domain. You could find the domain from your graph as well, but you can also do it with what you've solved here for your vertical asymptotes. Your domain excludes your vertical asymptotes. So we can do what we normally do for domain, which is draw a number line, plot our asymptotes on those number lines, and our function exists everywhere except at the vertical asymptotes. But one thing that we have to remember is that we have a hole at -7 as well. So in our domain, we can't forget that. We can't forget the hole. So it's important to not forget, if you cancel out a common factor, it's important not to forget that value, because your function doesn't exist there either. It originally would have been a vertical asymptote, but you got to cancel it out, but it's still, your function doesn't exist at that number. Because if you didn't cancel it out, it still wouldn't exist. You're still dividing by 0, but technically cancel it out. It's a little bit of a fuzzy area. So you just remember your domain would exclude any holes as well. So you have these big open circles, but your function exists everywhere else. So this would be this interval, this interval, this interval, and this interval. So our first interval going from the right to the left would be -infinity to -7. Whoop, -7, there we go. We don't include anything, so it's all parentheses. Then we have -7 to -1, -1 to 3, and 3 to infinity. So these are all the intervals where our function exists, and then you just want to connect them all with unions. So there is our answer for our domain. -infinity to -7, union -7 to -1, union -1 to 3, union 3 to infinity. So, all right, now the last thing we want to do is look at the range. So we're going to go ahead, go back to our slide so we can look at that graph, discuss the range, then we'll go ahead and write it down as the last part of our notes here. So here's our graph of our function here. We see that our domain was separated by those values there, -1 and +3. And we do have that hole there at -7. So that's what it was when we saw it in the beginning. That's how we got there. And we definitely see that looking from left to right, our graph was kind of separated here. And if we look, to this part of our graph right here, the most left-hand side, that it is going to stop kind of at 0 if we're looking, up and down instead. It does kind of stable off at 0. And if we look to the other end of the graph as well, we see our graph is also tending towards 0 here. We imagine that it's never going to cross that horizontal asymptote. But if we look in the center, yeah, that graph goes right through the horizontal asymptote. So from the left to the right, we have breaks. We have the vertical asymptotes. But going from up and down, we see that there's at least one value of y for every single value of x, except for the vertical asymptotes. So for all of the valid values of x, there's going to be a value of y. And we see that it's going off to positive and negative infinity. So this means that our range is negative infinity to infinity for a function like this. So let's go ahead and just write that in our notes to finish up this problem. All right, so our range, negative infinity to infinity, this was found from the graph. So looking at this problem again, we factored out that common factor, x plus 7. We found there was a hole at x equals negative 7. We found the x-intercepts, 2, 0, the y-intercept, 0, 2, 3. The vertical asymptotes were at negative 1 and 3. Horizontal asymptote was at y equals 0. We found that domain by excluding the vertical asymptote. And finally, the range. So there we go, finish up that problem for rational functions. Now let's go ahead and do the very last example from our review. All right, here's our last example, example 8. We want to solve the inequality. We've got x squared minus 41 is greater than 2x minus 6. So, all right, we're going to go ahead and go on over to our notes to work on this problem. All right, example 8, x squared minus 41 is greater than 2x minus 6. So we're going to go ahead, we want to solve this inequality. So looking at a problem like this is a polynomial inequality. Now we learned about rational inequalities as well, so I had to suggest reviewing the questions from section 3.7, or the one question from section 3.7 that was the rational inequality. In the exams, you can have either one, a rational or a polynomial, so it is good to study both. But here we are, we have a polynomial inequality. So we're going to go ahead and solve this. Now we have some guidelines for solving a polynomial inequality. Your first step is that you want to bring everything to one side. And we're going to bring everything to the left-hand side. So here is step 1. We're going to go ahead, we're going to subtract 2x from both sides and add 6 to both sides as well. We're going to get rid of everything on the right-hand side and bring everything over to the left. So this, as a result, will give us for step 1, we would get x squared minus 2x minus 41 plus 6 is greater than 0. Now, x squared minus 2x, those are not common or like terms, so you would not combine those, but we have negative 41 plus 6. So we're going to go ahead and combine those because they are like terms. So we get x squared minus 2x, negative 41 plus 6 would be negative 35. So we have a polynomial here, x squared minus 2x minus 35 is greater than 0. We have a quadratic function here, so we can factor. That is very exciting. We can see here that we can factor it using really any factoring method that we like. You can use, kind of reverse foiling, the square method, triangle method. You can also use a quadratic formula, even for a problem like this. So as a reminder, one way to factor, we saw this in one of the previous examples, but one way is that you can have, x squared plus a plus b times x plus a times b. You want two numbers that multiply to negative 35 that also add to negative 2. So you can think of all the numbers that would multiply out to negative 35. There's not a whole lot. It's really 35 and 1 and 5 and 7. So we see that 5 and 7, if we subtract them, their difference is 2, which is that number there in the middle. And 35 is negative, which means that one of those numbers has to be negative. So we're pretty sure it's going to be 5 and 7. And we can kind of think this through. Negative 35, one of them has to be negative. We have a negative 2 there in the middle, which means that the bigger number is the one that's negative. So in this case, the two values would be negative 7 and positive 5. So this would factor, and this is now step 2 as well here. This would factor into x minus 7 times x plus 5. greater than 0. So there we go. Now we have our two factors. At this point, you want to find the zeros. In step 2, you want to factor and find the zeros of your polynomial. So to find the zeros, you would set each one of these factors equal to 0 separately to find the zeros. So you'd have x minus 7 set equal to 0 and x plus 5 equal to 0. Now we can add 7 on the left to get x equals 7, subtract 5 on the right to get x equals negative 5. So the zeros are negative 5 and 7. Now in your guidelines for solving polynomial inequalities, we have at step 3, you want to find the intervals. And finding the intervals is always handy when you draw out your number line. You draw out your number line, you put the values negative 5 and 7. And we can look at our problem and we see that our inequality is strict. It is strictly greater than, meaning that it cannot be equal to the values of the zeros. So that means that negative 5 and 7 do not get included, which means that we have these big circles around 5 and 7, and we would have parentheses in our interval. It's always good to determine in step 3 whether or not you're going to have parentheses or brackets in your intervals so that when you get to your answer at the end, you just double check your answer instead of trying to fix anything. So step 3, negative 5 and 7 are not going to be included, which means that we are only having parentheses in this case. And we see that our interval would really be anywhere other than negative 5 or 7. So we've got one interval here, another here, and our last one here. So our intervals be negative infinity to negative 5, negative 5 to 7, and 7 to infinity. Now, we're not labeling a domain or anything, so we don't need to write unions. We can just write commas. Although if you wrote unions, I wouldn't mark you off for anything. But you don't need to have them. You're just listing the intervals. So how was step 3? We list the intervals. Step 4 is you're going to create the table. Now in section 3.7, we went over how to create the table. But what you do, as a reminder, is that in your first column, you would write sign of. This is your very first column. And you're going to have quite a few rows. So you kind of want to draw the first kind of lines here. You want to draw sign of, and then draw line down, line across. And across the top row, you're going to write in your intervals. So they're each going to be a column. So you'll have negative infinity to negative 5, negative 5 to 7, and 7 to infinity. I did the best I could there with figuring out how big those are going to be. So that is your first row, and then your first column, you will write the factors. We said our polynomial factored into x minus 7 and x plus 5. You're going to write each one of those factors. So we've got x minus 7, make a row for that, and x plus 5, make a row for that as well. Then that last row goes to the polynomial, which you found over here from step 2. So this right here was p of x, the polynomial. So really, this is saying that you want p of x greater than 0. P of x is that whole x squared minus 2x minus 35. That's p of x. So we're going to write that in down here, p of x. So now that you have your table created, how this works is that you will pick a test point from every interval that is listed here. And you will test that point within the factors, because the combination of the factors makes up p of x. So if you want to refresh on this, you can always look to section 3.7 where we go through this more. But all right, so we have the interval negative infinity to negative 5. We just want to pick a number in that interval. Doesn't need to be hard, make it as easy as possible. I think that's going to be a negative 6. Then we have negative 5 to 7. I think the easiest number in there is always 0, but you may like 1. Then we have 7 to infinity. Let's go ahead and just pick 8. So you want to make them as easy as possible. Then we're going to use our test points to plug into our factors. So using -6, we would have -6 minus 7. That's a negative number. And then -6 plus 5. That's still going to be a negative number. So our polynomial p of x has a negative number times a negative number on the interval negative infinity to -5. And two negative numbers create a positive number. So p of x is positive on the interval negative infinity to -5. All right, moving to the next column. Our test point in this column is going to be 0. So we have x minus 7. So 0 minus 7 would be -7. It's a negative number. 0 plus 5 would be 5, which is positive. Then p of x is a negative number times a positive number, which creates a negative number. Then our last column, we have that x is equal to 8, or that's our test point. So we have 8 minus 7 would be positive, and 8 plus 5 would also be positive, which means that p of x is positive on the interval 7 to infinity. All right, so we figured out when p of x is positive and when it's negative. We want to remember that what we're looking for is when p of x is greater than 0 or when p is positive. So that's what this is saying right here, positive. So we see p of x is greater than 0 here and less than 0 on this interval. And this was the solution we're looking for. Where is p of x greater than 0? And the answer is in these intervals right there. And you will actually write that for your final answer. For your final answer there, you would write negative infinity to -5. And now since you're listing kind of your final intervals, you would use a union. So we have negative infinity to -5, union 7 to infinity. So there is our answer. That's what we would write. You always want to check to make sure that your endpoints are correct, which in our case, remember we had a strict inequality. We said it had to be greater than 0, just positive. So it couldn't be the values over 0, couldn't be -5, and it couldn't be 7, which means that you have to use parentheses. So in our final answer, we do have parentheses. You always want to check, make sure that that's correct. So all right, there would be our answer for a polynomial inequality. As a reminder, you can have a shot at getting a polynomial inequality or a rational inequality, so it'll be important to study the one that we went over from section 3.7 as well. All right, let's go on back over to our slides. All right, so that was actually our last example there, example 8. So that was all the examples for your exam 2, which is coming up very shortly. So as always, good luck studying for your exam. If you have any questions or would like to visit office hours or anything like that, you can always let me know. We can review anything for your exam. All right, good luck everybody on exam 2, and I'll see you all in chapter 4.